Just Control L. Okay. All right. So yeah, we'll begin with our last but one unit, which is solution thermodynamics. After this, we'll talk about interaction between solids and gases, and that should be all. Um, so, in our last module, we talked about how the energetics change when two gases mix, right? When there is no interaction of gases, when there is interaction of gases, and how does it lead to change in enthalpy, change in entropy, and change in the overall Gibbs energy, and of course the equilibrium conditions thereof. So the approach is to take similar formalism and apply it to liquids. Right, this is typically dealt in chemistry as physical chemistry, in chemical engineering is chemical thermodynamics, and the same principles we also apply in materials thermodynamics. You might wonder what are we doing about liquids, right? Because we always deal with solids and all that. But the approach is that you start with the simplistic things, that's the gases, and a little more complex thing, that is the liquids, and then you get into the more complex things, which are the solid phase. But having said that, when we talk about liquids, that we generally refer to normal temperatures, and refer to ethanol, methanol, water, and some of the benzene, chlorobenzene, and things like that. But then when you take the domain of your temperatures to 1500 degrees Celsius, 1600 degrees Celsius, and more and more, a higher temperature, then it starts making sense as to how it would affect a materials engineer or a materials scientist, because at those temperatures, the stuff that you're always been thinking about solid phase are going to be liquid, and in materials processing, liquid metals is extremely important. Not as much in ceramics, but more so in materials, in metallurgical engineering. So the idea of solution thermodynamics, you don't really have to limit it to only normal temperatures. The same thing can be applied to a higher temperature, and then starting to understand that those concepts from normal temperature point of view is the way forward. That's making things from very simple things to more complex aspects. So this is a typical outline. We'll talk about Raoult's law and Henry's law, how these two are different, going from a simple liquid to a slightly complicated mixture of liquids. And then, much like the gaseous things that we spoke about, we talked about the thermodynamic properties of solutions, much like what we had in mixing. These two are kind of a similar thing. And then we talk about thermodynamics of non-Raoultian solutions, and then another kind of solution, that's regular solutions. That's what would seal it off. And let's see how we can go about that. So there are not many pictures here, but I hope I could draw something here. And that's not important. You'll have to pay attention to what I say. Now, if you have a glass of liquid, and it's open to atmosphere, would you be able to know, blindfolded, that there is some liquid there? Most likely not, when you think about things like water. If there is a glass of water on the table, and then you are inside the room, but blind, you'll be able to know if there is water, perhaps not. But then if there's a glass of alcohol, or say gasoline or petrol, would you be able to understand, or would you be able to recognize that there is some specific kind of liquid is there? Perhaps yes. All right, even if you're blindfolded, because you're able to sort of sense the smell of that liquid. The question is, since water doesn't have a smell, that's why you're not able to sort of uh, identify that whether there is an open tumbler has water or not. But then if it is petrol or alcohol or something, but you used to that smell, and then you're able to spot it out. That means there is some amount of vapor of that liquid phase that's there in the atmosphere in the nearby region. And that would be called a vapor pressure. The pressure exerted by the liquid vapor that's there in the atmosphere. In a way, you could see that there is an equilibrium between the liquid that's contained in the liquid state, at the same time the vapor that's in the atmosphere. There's an equilibrium in that. Okay, and how does that happen? Because from the liquid, some atoms or molecules actually go to the vapor state. They come over the attractive forces that's there in the liquid, and then they go into the vapor state. All right, and that rate of evaporation is actually it can be proportional to the saturated vapor pressure of a particular liquid. For example, if you compare a thick oil versus petrol, thick oil is talk about a mineral oil, or even if some oil which has a specific smell, right? And you take the same amount of oil in a tumbler, in a glass, vis-a-vis the same amount of same volume of petrol in a glass, and keep them side by side. Even then, you'll be able to sort of detect the petrol than the other mineral oil. So it's a function of the saturated vapor pressure, and some much volatile substances have a higher saturated vapor pressure, and the rate of evaporation would be much higher in those cases. Okay, so we can generalize that in the sense that the rate of evaporation of a particular type of liquid A would be proportional, some kind of a proportionality constant multiplied by its saturated vapor pressure, right? And if this one is higher, the rate of evaporation of that particular molecule would be higher. And the same way you can write it for another liquid which is again proportional to its saturated vapor pressure. Now these we are talking about a pure liquids, for example, some water and alcohol, and then we're trying to see what's the rate of evaporation of water, of alcohol. Okay. And this PA0 is usually denoted as the saturated vapor pressure of the pure liquid A. This when there is nothing else in between. There's only that type of liquid. Okay. And you can define like that PA0 and PB0, which PB0 is the saturated vapor pressure for liquid B. All right. Now consider a case where we have a liquid A, and we add some amount of liquid B into the liquid A. And how would that change the evaporation behavior? Okay. Now, what essentially happens that if there is this, if you look at the blue balls, these are the solvent molecules, right? These are like spread uniformly. And the red or the magenta, is it magenta? Yeah. Okay, the red color balls are, let's say, the solute, or solute meaning the minor phase that you're adding into the major phase. Okay. As an effect, how would that change the vapor pressure? Okay, you think of it as a surface phenomena, right? Evaporation. Let's say if you're talking about evaporation of the particular molecule from the liquid state and to the vapor state, would be proportional to the kind of molecules that is available on the surface, right? Now, when it is pure A, then all the molecules that are available on the surface is only A. Now, if you add 1% or 5% of B onto A, then on the surface you have now 95A and 5% B. So eventually what's going to happen is that the vapor pressure of A, okay, would be reduced by the amount of availability on the surface. And the same is, the surface composition would essentially be the same as what the bulk composition of A and B is, depending on how much of B you're adding into A. So the point I'm bringing up is that it's a statistical chance of a molecule from a particular container to get evaporated is eclipsed by the amount of B that you have in the liquid. Okay. In the same way, you'd see that the amount of B also is going to be eclipsed by the same similar amount of the presence of A. So if we want to put things in a mathematical way, you'd see that it actually is a function of the mole fraction of A that you have. Initially in a pure situation, you have this XA that was completely a full A, that was XA was 1. And now XA is a fraction which is less than 1 because you have another component that is added to the solution. So it's going to be reduced by this much amount, which can vary from 0.5, 0.7, 0.9 or 0.95. Likewise, this PA in the earlier equation, you had this vapor pressure of the pure substance. Okay, and that pure substance now would be reduced to the vapor pressure of the particular liquid A in a mixture, which is an AB mixture. Okay, so since it is in a mixed state, we would call this PA and not PA0. Likewise, the same rate of evaporation of component B in an AB mixture would be written like this, which is multiplied by XB, and K2 is the earlier constant that we had in a pure B situation, and the PB0 was in a pure B situation. Right now it sort of reduces to PB, right? So this is a simple proportionate kind of change in the in a liquid, and that you can simply write as PA. That means the vapor pressure exerted by the component A in the mixed situation, mixed thing of A and B, is actually XA into the saturated vapor pressure of pure A. Likewise, PB would be XB, the mole fraction, multiplied by the saturated vapor pressure of component B. And this is called Raoult's law. It's as simple as that. It's kind of very proportional. And if you have to explain that in a graphical form, you can sort of put it like this, where this one says this is the pure component A. I'm sorry, B, this pure component, and in that B you start adding A's to the point where here it is pure A only. There's no B here. Okay, so anywhere between this line and this line, it's always A and B, and the proportion would depend on how much it is from A. If you talk about this point, this is 50% A and 50% B. If you talk about this point, this is 25% A and 75% B. Talk about this point, this is going to be 75% A and 25% B. All right, and these points here, I've taken this figure from Paula Atkins' book, and they write PB0 as PB star, so it's pretty much the same thing. So this is the saturated vapor pressure of component B in its pure state, and this is the saturated vapor pressure of component A in its pure state, and this line is the partial pressure of B in the mixture. This is the partial pressure of B in the mixture. It means this partial pressure is same as the saturated vapor pressure of B in its pure form when there is no A inside. But when there is little bit of A, like talk about this one, this perhaps is 95% B and 5% A. So the partial pressure of B is actually 0.95 multiplied by PB star or PB0. Likewise, when you have B gradually reducing, then its partial pressure is coming down. So much so that when there is zero, this partial pressure is zero. Like the same thing, you can talk about the partial pressure of A, where in here at 100% liquid A, the partial pressure of A would be completely PA0. And as you keep on adding B, the partial pressure of A gets reduced to the point where in pure B, the partial pressure of A is zero. Now these are the individual partial pressures, and the total pressure of the system is simply the addition of these curves. That means when you talk about the total pressure at this composition of 5% A and 95% B, it will be this much, that's partial pressure of A plus partial pressure of B, which B is increased by this amount, which is the point here. Likewise, if you keep on adding these two curves, you'll see that the partial total pressure is actually changing from the saturated vapor pressure of B in its pure state, and when you keep on adding A, then it sort of reduces to the point where here the total pressure is equal to the saturated vapor pressure of A. Now this curve, this line is going to go, reducing, because it's simple. The saturated vapor pressure of A is lower than the saturated vapor pressure of B. So when you keep on adding A into B, the total pressure is always going to be reducing. So this is what the theoretical graph would look like. And if we have to look at a practical, a real graph, let's look at this one, where it talks about benzene and methyl benzene. These are two similar kind of liquids, and that's can be said as an example of a Raoultian liquid mixture. And you see that this is the partial pressure of methyl benzene from 0 to complete methyl benzene at this point. This is increasing this. And likewise, when you have pure benzene here, and then you keep on adding methyl benzene, the partial pressure of benzene sort of reduces to the point where in methyl benzene, the partial pressure of benzene is 0. And when you add these two curves, you get this curve, which is the total pressure in a mixture of methyl benzene and benzene. This is as good as it gets in terms of mimicking a clear theoretical sort of a formulation. They're very rare, of course. You will still have materials which sort of provide this kind of behavior, but they're only handful. Typically, you'll see that materials of similar nature, liquids of similar nature, would sort of give this kind of a behavior. Right. Now, these are ideal situations. All right, this is the basic situation, ideal situation, but it's based on only statistics and mathematical mixtures. You can say that it's a mathematical mixture. But then, what happens when you have two liquids, liquid A and liquid B, and they have some sort of interactions between them? When we talked about Raoult's law, then it's sort of indicative that they do not react with each other. Right? Simply a statistical mixture or a mathematical mixture. Like we spoke about the mixing of gases which do not react. Now, for example, we talk about argon and nitrogen, argon and krypton, these kind of gases mixing with each other. And since they do not have affinity for each other, the enthalpy change, we sort of figured out there's no enthalpy change. So then it's just the statistical nature of the changes because of the mixing, because of distribution of two different types of materials, right, in a gaseous state. Likewise, it was Raoult's law talking about the mixture of liquids um, when the two components do not have any interaction of any affinity for each other. Now, coming back to a situation where A and B have some sort of affinity. For example, there must be some force which act between the similar molecules, which is the interactions, the energy between similar type of molecules, A, or B, the cohesive forces, right? Now, if these interactions are, for example, higher in energy than the heterotype interactions, for example, the energy between A and B, if this the AA type interactions are stronger than AB type interactions or weaker than AB type interactions. Okay, both are possible. And likewise, the BB type interactions, they're stronger than AB type interaction or weaker than AB type interactions. And in such a case, then what perhaps could happen that you have a statistical distribution of B in A, and for example, if AB interactions are stronger, then when A is trying to evaporate or leave the liquid phase and tries to go into the gaseous state, because of the stronger A and B interaction, it might be starting to pull it off, right? And which would affect in a way that the partial pressure of A is not going to be as high as it would have been with the absence of the AB type interaction, right? That means the partial pressures are going to be influenced by the extent of AB interactions and A type interaction or BB type interactions, right? And the simple way of looking at it is that if the hetero interactions is stronger, then they'll try to pull the molecules from going into the vapor state. If there are weaker interactions or the homo interactions is stronger, then perhaps they could easily go to the higher state. Or if there's a repelling interaction between A and B, then perhaps it'll allow it to go to the vapor state much faster, much easier way. So that is the aspect which was not there in the Raoult's law, and that aspect when we're considering, we are calling it Henry's law, by English scientist Henry, William Henry, okay. And he figured out these interactions, and these are typically that happen in a dilute solution case. For example, if you have only some percentage of B in a large percentage of A, or vice versa, when you have small percentage of A in a large percentage of B. For example, a case in point would be like a 5% A and a 95% B, or 5% B and 95% A, and in that region, that sort of solutions we have. And if there are hetero interactions and homo interactions which are different, then Raoult's law would not be applicable, right? And you could see that this is what is written here in some sort of a mathematical form, wherein we've said that the rate of evaporation of A would, in a prime case, would be eclipsed, or it'll be deviating from the intrinsic evaporation rate of A because of the interactions of AA and AB. Okay, so likewise we have written a term which PA is a ratio of the relative interactions because of the presence of AB or AA type interactions into XA and PA0, which is what is coming from the Raoult's law part. So eventually we could write as PA is Ka XA, the partial pressure of A is some constant into the mole fraction of A, and PB is another constant into the mole fraction of B. All right, and this can be given in a sort of graphical form, where you have an example of say acetone and chloroform, right? And if you look at it, it's almost like the Raoult's law kind of form, in the sense that if you look at the dotted lines here, So if we are looking at the partial pressure of okay, first is the P star or P0 is the saturated vapor pressure of acetone when it is completely acetone. There's no chloroform here. And here it is all chloroform. This is P0. That's the saturated vapor pressure of chloroform. Now, in this condition, if we start adding in acetone, we start adding chloroform. What can happen is that the partial pressure of each of the components will change, and as would be the total pressure. The total pressure is of course not given here. So the partial pressure of acetone in a mixture of acetone and chloroform is supposed to go like this dotted line as per Raoultian behavior. If the behavior was Raoultian, then the partial pressure of acetone would have come like this, right? Likewise, the partial pressure of chloroform would have gone like this, like followed this dotted line, which is indicative of Raoult's law. But actually what has happened is that when you add a little bit of liquid into a little bit of chloroform in acetone or acetone in chloroform, these are the measurements, the bold lines, the solid lines are actually the measurements of the partial pressures each of the components in the mixture. Like for example, this is going to be what, 20%, 40, 60, 80, yeah. So this 20% chloroform and 80% acetone is actually giving you this point as the partial pressure of acetone in this 2080 mixture, which should have been as per Raoult's law here, but then the point is here. And this is an experimental point. Likewise, you have experimental points here, here, and here, and here. All right. So you would see that it's kind of forming a curve. Right, and the same thing you can see for the chloroform also. It's sort of forming a curve. Right. So for that, in the dilute solution region, if we were to see a little bit of acetone in much chloroform, you'd see that we're talking about this region, and the partial pressure of acetone should have been like this, so it should have followed Raoult's law like this. But on the contrary, it's following a behavior like this. So for this region, if we were to find a straight line to this behavior, you would see that this is the line which actually defines the dependence of the partial pressure of acetone in the acetone chloroform mixture. So essentially, this curve, this straight line becomes this straight line. Likewise, in a dilute solution regime of chloroform in acetone, that's a lot of acetone, a little bit of chloroform, and you like to see the partial pressure of chloroform, how does it change? It should have been this, but then actually it has become like this. So if we consider the dilute solution regime of chloroform in acetone, you would see that this is the regime, and if we were to pick an equation for that, then you would see that this line pretty much defines the initial behavior of a dilute solution of chloroform in acetone. So these actually these curve and this curve actually are the forms. PA is Ka into mole fraction and Pb is Kb into mole fraction, and this is what is Henry's law. So while the ideal behavior is Raoult's law, when there is a behavior which is a deviation from Raoult's law, that could be called Henry's law. Right, and here this is where everything is sort of trying to pull it down. So you see that the partial pressures are typically lower than what it should have been in a Raoult's law situation. That's why these are called behaviors of negative deviation from Raoult's law. This is a Henryan liquid which has a negative deviation from Raoult's law. Right. On the contrary, you see some examples I haven't got here. You can see examples where instead of the real curve forming like this, you'd see the real curve on a convex side. Okay, and this one also would be a convex side, which would see that it's a positive deviation from Raoult's law, in that the AAB, or the two different types of liquids that we're considering in this mixture, they don't like each other. They have a repulsion for each other, so that there's a positive deviation from Raoult's law, right? Okay, talking about some couple of uh, thermodynamic terms which might be useful for us going forward. I hope you guys are conversant with the term fugacity, right? In fugacity is a replacement for pressure in non-ideal situation. If I have to say that in a most simplistic terms, for ideal gases we can write dGs RT dl and P. That's from this equation, and if you want to make it a slightly expanded form, this is the change in Gibbs energy is RTL and P2 by P1. These are the two pressures. Okay, and you can say that is a it's in a linear function of the pressure in ideal gases. But for non-ideal gases, in order to make this equation linear, okay, we replace something, this P2 by P1, or the P, by a term called F, which is called fugacity, right? Typically, when F by P is sort of 1, then this P becomes 0, right? So in a way, you could say that to replace the P term in this equation, and still keep it linear, okay, we just change P by a term which is called fugacity, right? And there's another term which is called activity. Okay, so this activity is a comparison between the fugacity of the component I normalized by the fugacity at the standard state. Right, it's as simple as that. Or that's for gases, but then we are more concerned here about liquids, condensed by Pi0, which is the partial pressure of the component I normalized by the partial pressure of the component I in its pure form. And you'd see that this is nothing but mole fraction. Okay, so in much of the case you could say that AI is Xi from the Raoult's law situation. Activity is simply as mole fraction when there is no other forces acting between two kinds of liquids that we have. So activity is mole fraction, which is another expression of the Raoult's law. But then the activity is slightly changed from mole fraction. That is sort of it's different from an analyzing factor, uh, where Henry's law comes in, which brings in the terms which contains interaction between two type of materials of the mixture. So we could write Henry's law at AI is some constant Ki multiplied by Xi. And this is another expression of Henry's law. All right. So if there is something like Raoult's law and then Henry's law, and Henry's law takes into account the interactions between different types of liquids, molecules, then it would be really nice to be able to quantify, or delve deeper into what's the type of interactions, and how can you get a hang of what kind of interactions are happening, and are there terms for that. So there's a term actually that's called the thermodynamic activity coefficient, TAC. That actually defines you know how different it can be from a Raoultian from how a Henryan liquid can be different from a Raoultian behavior, and it sort of gives you some indication for that. And here we talked about AI is KIXI. This KI term is actually what is called the thermodynamic activity coefficient, or we generally write that as gamma I, which is normalization of AI normalized by Xi. AI by Xi, that's the gamma I term. right? And this, if the gamma I is greater than 1, okay, the component is said to exhibit positive deviation from Raoultian behavior. So the example that we had here, it's a negative deviation from Raoultian behavior, which tells you that gamma I, or gamma of each of this component, must be less than 1. Had it been more than 1, the curves would have been, slightly concave, or yeah, convex. This is concave, this should have been convex kind of situation. Right. And likewise here, the gamma is less than 1, the component says to exhibit negative deviation from Raoultian behavior. Okay. And these deviations, are positive or negative, are actually related to the extent of um, um, the interactions between AA, BB, and AB, and how they are different, how they compare with each of these types of interaction, AA or BB or AB. These are the two homo interactions, and this is the hetero interaction. Right? Okay, so we'll talk about yeah, we'll keep it here. We'll talk about other questions. Should we stop it here and take questions, or you want me to go for maybe another concept? Okay, let's keep it here today, and then discuss a few questions. I'm stopping the recording. Okay, and then